Karnaugh Maps. We have seen how truth tables can be used to represent any Boolean function, and how the sum of products form can be used to represent and realize any function. A remaining question is, how can we ensure that our sum of products form uses the fewest terms, and therefore gates, as possible? We will address that now by looking at Karnaugh Maps. Karnaugh Map. A Karnaugh map consists of cells. Each cell corresponds to a row in the truth table of the Boolean function, so there are as many cells in the map as rows in the truth table. Each cell will contain either a 1 or a 0, depending on the value in the corresponding row of the truth table. The cells are arranged so that all the cells corresponding to rows where an input variable is 1 are adjacent. Therefore, the cells form a region or zone where that input variable is 1, and a region where that input variable is 0. In the slide, we have highlighted the region for cells where the input variable a is 1. There is a pair of regions, one for 0 and one for 1, for each of the input variables. In this slide, we have highlighted the region where the input variable b is 1. Notice that this region partially overlaps the region where the input variable a is 1. A moment's thought makes this obvious. Half the rows of the truth table where a is 1, b will also be 1, but in half of them a will be 0. By creating such a region for each variable and ensuring they never overlap completely with another, we create a grid where each cell corresponds to a row in the truth table. For convenience, we have labeled each cell with the bit pattern for the corresponding cell in the truth table. It is important to see that each cell differs from its neighbors, left, right, up, and down, by the value of only one variable. We could say that a cell is adjacent to another if the bit pattern for the corresponding value in the truth table differs by only a single value. This is a vital property of a Karnaugh map. This definition of adjacency means that cells that are diagonal neighbors of a cell are not adjacent to it. Wrapping round. Given this definition of adjacency, we need to see that cells at the top of the map are adjacent to ones on the bottom of the map, and those on the left are adjacent to those on the right, so that the cells highlighted in green are adjacent, as are the cells highlighted in yellow. The map can be considered to be drawn on the surface of a torus, although this is harder to see than to remember the adjacency of cells on the sides. Example. The easiest way to understand the Karnaugh map is to use an example. We have chosen a simple example of a truth table with only 4 ones. For each of the ones in the truth table, we place a 1 in the corresponding cell of the Karnaugh map. For convenience, each cell on the Karnaugh map has been labeled with the bit pattern for the corresponding line of the truth table. In this case, we have identified the 1 in the truth table where all the inputs are 0 and placed a 1 in the corresponding cell of the Karnaugh map. In this way, we can proceed to fill in all the ones from the truth table. Fortunately, in this function, there are only 4. Finally, we put a 0 in all the other cells. We have done this for completeness sake. Frequently this step is omitted as it can make the next steps clearer. Each of the cells that have a 1 in them represent a min term in the sum of products representation of a function. We want to find the implicants of this function by factorization. On a Karnaugh map, factorization is trivial. We only need to merge adjacent cells to create a factorized implicant. In our example, we can merge the red and yellow cells to form an implicant. This new group of cells is in the sets where A and C are 1, but B is 0. It straddles the boundary between the sets where D is 0 or 1. This implicant, therefore, would be written as A and not B and C. You can easily check that this is an implicant of the original function by writing out its truth table. One of the cells is also adjacent to the green cell. This cell should be able to be included in an implicant. However, in order to correctly represent implicants, groups of 1s must be rectangular and have sides of length 1, 2, or 4. If this cell was added to the red group, then the shape formed would not be rectangular. However, a cell may be included in more than one group or implicant. Therefore, the cell in question may be grouped with the cell above it to form a simpler implicant. We have drawn this in the more common way of enclosing cells that form an implicant in a ring. Notice that the cell in the cyan ring cannot be included in any simpler implicant since it has no neighbors. This means that the groups we have formed are a set of prime implicants and cover all the ones in the Karnaugh map. We can use them as a sum of products representation of the function with confidence that this is one of the minimized sets of prime implicants. In a more complicated example, we have chosen a function with more 1s in its truth table. We have transferred these to the Karnaugh map into their corresponding cells. The zeros have been omitted to help with the clarity of the map. We have then selected a way of grouping the cells that minimizes the number of groups, while at the same time covering all the 1s. In this case, there are several groups that overlap. There is one group of 4 cells, the blue group, and there is one group that wraps over the edges, the magenta group. The members of a set of prime implicants that minimizes the number of prime implicants while at the same time covering all the 1s are known as essential prime implicants. There may be more than one set of essential prime implicants, as we could see from this example. We can extract the prime implicants represented and write them in the familiar form. We have color-coded the sum of products form to help see the correspondence between groups on the Karnaugh map and implicants in the sum of products form. Conclusion. A Karnaugh map consists of a cell for each line of the truth table. The cells are specially arranged so that adjacent cells differ by only a single input variable. Once the Karnaugh map has been filled out using the truth table or another Boolean logic function, then the cells containing ones can be grouped. By forming a grouping with the fewest and largest cells that cover all of the ones, we can find a set of prime implicants. These prime implicants can then be extracted in a sum of products form. It is important to note that we have only considered Boolean functions with 4 inputs. Boolean logic functions of 5 and 6 variables require us to consider a cuboidal structure which wraps at the edges. Functions of 7 and 8 variables require us to consider a hypercuboidal structure which wraps at the edges. Additional input variables add additional complexity, and this method is only practicable to 6 or perhaps 8 input variables. Fortunately, there are computerized methods that allow us to create efficient representations of Boolean logic functions of nearly arbitrary size.